Hi, I'm Vojislav Dukic and I'll tell you about Photons, a system that improves performance of today's serverless platforms. This is a joint work with my colleagues from ETH Zurich, Rodrigo, Bruno, Ankit, Singla, and Gustavo, Alonso. All major cloud providers offer serverless platforms. Although these platforms present a significant leap forward in terms of flexibility compared to traditional virtual machines, there is still substantial room for improvement, especially when it comes to handling highly concurrent workloads. Let me demonstrate this inefficiency of today's serverless platforms on a simple example. Consider an image classification workload. Every front-end request that arrives to serverless platform carries a small resolution image that needs to be classified. For classification, we use a TensorFlow model pre-trained on the ImageNet dataset. Note that serverless functions are rarely invoked in isolation. Due to serverless capability to quickly allocate and release a large amount of resources, serverless computing is perfect for handling bursty workloads with a large number of concurrent requests. As an example, we consider processing a flood of image classification requests. Looking at the execution of a single invocation of the image classification workload in more detail, we observe that every single request asks for a dedicated execution stack. That includes a container, runtime, and libraries like TensorFlow in this case. Also, it asks for a machine learning model that must be fetched during execution from remote storage. Finally, the invocation requires a bit of request local operational memory for computation, storing the image, and creating a response. In reality, many invocations of this workload will be invoked in parallel. Here, each vertical column presents one invocation of the same function and shows all the components an invocation requires. Although most of the components remain the same across invocations, each request creates an isolated execution stack. Not being able to share common components across invocations on today's platforms causes all sorts of problems and inefficiencies. Creating each separate stack wastes CPU cycles and takes time. Besides that, functions end up using much more memory than necessary. Also, note that in some workloads, certain parts of computation could be shared in form of intermediate results. For example, for the image classification workload, the pre-trained model fetched from a remote storage must be uncompressed and processed before it can be used. These models commonly require tens or even hundreds of megabytes of memory, and with sharing allowed, once the first function processes the model, others will be able to use it without any overhead. Ideally, we would like to share not only intermediate results, but all components that are common across invocations, including runtime and libraries required. More concretely, let us see how much exactly we can save. We implemented this particular image classification workload both in Java and Python and break down memory consumption into 4 categories. Out of these 4, runtime, libraries, and classification model can be shared. Depending on a particular environment, they comprise 70 to 90% of total memory consumption. On the other hand, only a small portion of memory is required for request-specific computation, in this case less than 30%. This motivated us to create Photons, a system that improves overall performance of serverless platforms by allowing runtime and data sharing across invocations. On production-level workloads, Photons achieve 30% reduction in cluster memory utilization. Also, as I'll show later, thanks to data and runtime sharing, Photons decrease the total number of so-called cold starts by 52%, which substantially improves performance, especially for short workloads. So what is the main idea behind Photons? How do they achieve reduction of memory utilization, cold start events, and improve overall performance? Performance improvement is achieved in 2 ways. First, using language-level memory isolation, which means that multiple concurrent invocations are hosted within the same runtime. Then the runtime guarantees that no unauthorized memory accesses are possible. This allows automatic sharing of libraries and runtime itself. Second, we extend the runtime with a shared data store that allows users to explicitly share objects and intermediate results. The shared store is isolated from the rest of the runtime and can be accessed only using a simple interface. Since collocated invocations can access shared objects concurrently, we provide a special photon locking mechanism that can be used for synchronization. Also, although our reference implementation relies on Java and JVM, the main idea behind Photons is not Java-specific and can be implemented in other runtimes. More details on photon locking mechanism and other runtimes are presented in the paper. Now, since each collocated invocation requires only a small amount of memory, while the rest can be efficiently shared, we call these invocations photons. Note that if a single photon is allocated in isolation, it is equivalent to today's serverless function invocations. It basically requires allocating the entire stack for a single invocation. On the other hand, contrary to traditional serverless functions, concurrent invocations implemented as photons can be collocated within the same runtime and thus reduce memory consumption and improve overall system performance. However, there is one problem with this approach. Language-level soft memory isolation is considered insecure compared to VM and container isolation when running untrusted code. We tackle this problem by combining only invocations that can trust each other. More precisely, we execute only invocations of the same function within the same runtime. The assumption here is that a particular function can trust at least itself. Let me illustrate this on an example. We execute 4 concurrent invocations. 2 of them are doing image classification, 1 does some sort of video conversion, and 1 accesses a database. Within the same runtime, we collocate only concurrent image classification invocations, while the rest is isolated using a strong memory boundary in the same way as in today's serverless systems. Collocating invocations that can trust each other is just the first step toward providing safe execution. As I will show, we must apply additional steps to guarantee data separation between collocated invocations. Let me now share more details on how to deploy Photons on a cluster of machines. When we deploy a function on Photons, we need to provide 4 inputs. First, function code and binaries must be provided similar to today's platforms. Since our reference implementation is integrated with OpenVisc and Java, the function code is provided as jar file. Second, users have to mark their functions as photon-friendly. If the function is not marked, it will always be deployed without collocating as a standard serverless function in an independent container with strong memory isolation. This is necessary for functions that process very sensitive data and cannot afford to trust even themselves. Third, users must provide the amount of CPU and memory required for a single invocation. We call these initial CPU and memory requirements. Provided these requirements works exactly the same way as on today's platforms. However, in addition to that, users must specify how much additional memory will be allocated for every additional collocated invocation. This is called a memory increment. Let me now explain how initial and increment resource requirements work. A single invocation requires 1 initial unit of memory and 1 initial unit of CPU. When an invocation of the same function is collocated within the same runtime, the memory allocation has to increase only to accommodate private invocation state, which is specified by the user as memory increment. Note that the memory increment is always lower compared to initial memory requirements. While collocation brings memory savings, CPU cycles required per invocation remain the same. This is why n invocations require n CPU units. Also, note that users have to specify only 1 parameter related to CPU requirements, and that parameter remains the same across all invocations. Since CPU and memory increments are different for collocated invocations, Photons require being able to set CPU and memory allocation independently. On many current platforms, serverless resources allocation is provided using a single slider for both CPU and memory. However, Photons ideally require 3 independent inputs for initial memory, memory increment, and CPU. Another important question is how to determine base and increment resource requirements. For every workload, CPU requirements remain the same as on today's platforms. They can be determined by running the workload, in this case image classification, for various CPU allocations. As we increase CPU allocation, the execution time improves, but at the same time the cost of resources increase. For this workload, the sweet spot is around 0.7 CPU cores. On the other hand, the memory requirements are determined by running one isolated invocation and measuring the memory consumption, and then collocate two functions and measure the difference in memory requirements. This difference is memory increment. In practice, though, we have to benchmark the workload with various inputs to determine the worst-case memory increment, since the size of private invocation state can vary based on the input parameters. In the paper, we show that this approach does not cause any performance throttling compared to running isolated invocations, as on today's platforms. Once we have all four inputs, jar file, photon-friendly flag, initial and increment resource requirements, we are almost ready to deploy a function. One remaining problem is that Java does not provide any memory isolation between invocations that are running within the same Java virtual machine. For instance, static fields are accessible for every part of the runtime, so if multiple collocated invocations use them, that can lead to inconsistencies and incorrect execution. Since we want to maintain the same abstraction as today's serverless platforms, where every request is completely isolated, we have to modify all global elements in the program that can keep state and replace them with a piece of code that guarantees isolation. Here we show how simple access to a static field X is replaced by a wrapper method that assures memory isolation. To support this transformation, we develop a preprocessor that automatically modifies static elements in Java bytecode and make the function photon-friendly. In the paper, you can find more details on the photon compilation process as well as memory isolation. Okay, so far we have all the inputs and the function code is made photon-friendly using bytecode transformation. Let us now take a look at the scheduling of photon functions. After benchmarking the image classification workload, we know that each invocation requires 0.7 CPU cores, 248 megabytes of memory for the first invocation, and only 29 megabytes for every further collocated invocation. For simplicity, let us also assume that photons are scheduled on machines that have 2 CPU cores and 2 gigabytes of memory. For the first invocation, we create a new stack on one of the machines. For the following concurrent invocation, we check if there is already a running instance of the same function and if the physical machine has enough resources to collocate an additional invocation. In this case, the machine does have enough resources because we can allocate 0.7 cores more and increase memory utilization by 29 megabytes. However, when an invocation comes but the machine with an active stack does not have enough resources, in this case insufficient CPU, a new stack will be created on another machine. Compared to today's platforms, in this particular case, Photons create only 2 stacks instead of 3, which reduces the number of stacks created, improves startup time, and introduces substantial memory savings. Now let us see what's the impact of using photons on a cluster of machines. We are primarily interested in 2 things. 1, how much resource can be saved using photons on a cluster? And 2, how are those free resources further utilized to improve overall serverless performance? First, we analyze how much memory can be saved on a single machine. As we increase the number of concurrent invocations that are collocated on one physical machine, we show how the memory consumption increases on the y-axis for various workloads. Intuitively, the lower the consumption, the better. Memory requirements are normalized across workloads so that the first invocation requires 1 unit of memory. For the baseline shown in blue, which is using today's platforms, memory requirements grow proportionally. For instance, 100 concurrent invocations require 100 units of memory. However, for all other workloads we tested using photons, there is always something to be saved, so the memory consumption is always lower than the baseline. For the video conversion workload, shown in the brown line, savings are relatively modest because the workload has substantial invocation local data and can share only the runtime. However, the rest, including the image classification, file hashing, and REST API calls, show substantial decrease in memory consumption using photons. As a reference, for 100 collocated invocations, photon implementation of image classification consumes 5 times less memory compared to using today's platforms. These savings were made only on a single machine. Now, how do photons impact a cluster of machines? How much we can save there? Note that the key to making sailing is to have a large number of concurrent invocations of the same function. Obviously, if the requests are not concurrent, they cannot be collocated and there is no benefit of using photons. In that case, photons are equivalent to current serverless platforms. On the other hand, the more concurrent function invocations we have, the larger the sailing will be. Fortunately, high concurrency is common for production serverless workloads. A recent study of production workloads from Microsoft Azure serverless platform has shown that less than 10% of all functions are responsible for 99% of invocations. Based on these insights from Microsoft Azure, we simulated a cluster of 100 machines. While the cluster utilization oscillates around 70% using today's serverless platform, shown in blue, Photons reduced that by 30%, shown in orange. Although 30% is substantial memory savings, note that it does not imply 30% less machines in a cluster. Recall that photons do not reduce the number of CPUs required. However, as I already mentioned, free resources can still be used to improve performance by reducing the number of cold start events. Let me first explain what a cold start is. When we schedule an invocation for the first time, we must spawn the entire stack with runtime and libraries, which takes time. Depending on runtime, creating a stack can last up to 300 milliseconds on today's platforms. Now, when an invocation finishes, we don't have to clean up the stack, but rather keep it in memory for future invocations. When the next invocation comes, we have warm stack already available, and the startup overhead reduces under a few milliseconds. Now, the key observation is that if we have more resources, we can keep more warm containers in memory and thus increase the probability of observing a warm start. Collocating of incoming concurrent functions and using free memory created by Photons to store warm containers led to 52% less cold start events on Microsoft Azure production workload. This is particularly important for very short functions that can observe an order of magnitude improvement in execution time just by avoiding a cold start. To summarize, sharing the runtime, libraries, and operation data brings 30% lower cluster memory utilization with 52% reduction in the number of cold start events, which is essential especially for short workloads. I should emphasize that Photons require minimal platform changes on the provider side and almost no changes to existing serverless workloads. Photons provide the same abstraction to users as today's serverless platforms. We hope that in future, serverless providers will recognize the opportunity for improving the performance of serverless computing and implement Photons on their platforms. With that, I would like to thank you all for watching. I'll be happy to answer all your questions in the live session during this year's SoCC.